So far, we have formulated the proposition which alternatively characterizes the greatest common divisor of A and B. Now we will prove this proposition. Now, first of all, the first order of business is to prove that the set S, defined this way, is not an empty set. S is non-empty. In order to justify this claim, we need to find at least one element in this set. Set S is the set of all combinations AM plus BN which happen to be positive. Suffices to find M and N so that this number AM plus BN is positive. Let M be A and N be B. Then AM plus BN is A times A squared plus B squared. B times N is B. That is, of course, bigger or equal than 0 because A squared is bigger or equal than 0 and B squared is bigger or equal than 0, but actually it is strictly positive because we assumed that A and B are not both zeros. A squared is 0 only when A is 0, B squared is 0 is only 0 only when B is 0, so the sum is 0 only when both of them are zeros. If at least one is not, the sum is strictly positive. Thus, what we found M and N, so that AM plus BN is positive. This is an element of set S. The set is non-empty. Thus, A squared plus B squared is always an element of S. And S is not an empty set. That is easy. Secondly, we want to prove that the smallest element of this set is indeed the greatest common divisor. So we say that T be the minimum element in S. It exists because S is a non-empty set of non-negative or positive integers. So we have the smallest element. We want to say that this is the greatest common divisor. What does it mean? We want to prove one and two from the definition of a greatest common divisor, the greatest in order to justify that t, which we just found it exists, is the greatest common divisor. We start with 1 from the definition. 1 from the definition is that our greatest common divisor, so we want t1 and 2 to what we want to justify, t is equal to ab. 1 from the definition is that t is indeed a common divisor of a and b, meaning t divides a and t divides b. Because of the obvious symmetry between a and b, it suffices to prove that t divides a by the same token, it will divide b as well. Well, Euclid's lemma, so we want to prove t divides a. Euclid's lemma allows us to write a as t q plus r. For some integers q and r, with r not exceeding t. What we want to prove, we want to prove that t divides a, which means that there is no r here. So we want to say that r is not just some integer between 0 and t minus 1, but 0. So 1/3 r equals 0. R is equal to 0. The argument which we apply will go this way. If r is not 0, then necessarily positive, then r is an element in S. And since we know that r is smaller than t, t was not the smallest. In S. So r bigger than 0 will imply a contradiction. T, which has been chosen to be the smallest element in S, turned out to be not the smallest. R, if positive, is smaller. R is always smaller than S, But if positive, we want to say it is still in S. S does not contain 0. It contains only strictly positive elements. All right, how do we do that? We write R is anyway A minus TQ from here. T, the smallest element in S, is an element in S. So we can write T as any element in S. We can write AU plus BV. A times integer plus B times integer. Every element in S can be written this way. Times Q. So we can write T this way because T is an element in S. It has been chosen the smallest of them, but anyway, it is one of them, so we can write it this way as any element. U and V are some integers. And we write it as A times 1 minus U plus B times V times Q. A minus U is an integer. 1 minus U is an integer. Because 1 is an integer and U is an integer. VQ is an integer. Because V is some integer, Q is some integer, product of two integers is anyway an integer. So it turns out that R can be written as A times an integer plus B times an integer. And it's assumed to be positive. So every element, again, look here, every element A times integer plus B times integer, which happens to be positive, is an S. Our R, A, which we can write as A times integer plus B times integer, if positive, is in S. But R is smaller than T, so T was not the smallest in S. This contradiction allows us to conclude that R is 0, which means T divides A. Because of symmetry, as I said, or by a similar argument, you prove that T divides B as well. So T, the smallest element is in S, is a common divisor of A and B. Now I'll prove two of the definition, namely, we assume of the definition of greatest common divisor, we want to prove that T is the greatest common divisor of A and B. So 2 from the definition is that C divide A and C divides B. We want to prove that the C never exceeds our T. What is going to be proved is a strong statement. Namely, we will prove that C divides T. Every divisor of a positive integer T is the smallest in the set of positive integers. So this is a positive integer anyways. Its divisor is going to be definitely smaller than the integer itself or equal to this integer. So that implies that C is smaller or equal than T. So if C is smaller or equal than T, then it may happen that C does not divide T. It may happen divides, may happen not. But if C divides T for a positive integer T, then the answer is definitely smaller. Therefore, I'm speaking about stronger. Let us do that. Form or sense from these two divisibilities, we can write C divides A, so we can write that A equals C times K, and similarly from this divisibility we can write that B equals C times, say, S for integers K and S, just some integers. Then let us write how our T looks. T was in S, so it is A times integer plus B times integer. I will say A times U plus B times V, some integers instead of M and N. I'm trying to keep notations close to what the book has. A U plus B V with some integers U and V. Every element of S can be written this way. So T included. A can be rewritten as CK U plus B, which can be rewritten CS V. And we factor C out. K U plus S V. While for K, U, S, and V are integers, so T is equal to C times an integer, and that is, by definition, of the divisibility, C divides T. In this way, that proposition, our proposition, is proved. It gives us an alternative characterization of the greatest common divisor of two integers. not both zeros, as the smallest positive integral linear combination of these integers. Automatically, as I said in the previous video, that implies theorem 1.2. There is a small irregularity here which may be addressed. Namely, we proved a stronger statement at the moment, and analyzing this proof again, we can derive what the book calls corollary 1.3, which is an alternative definition, yet alternative definition of the greatest common divisor. So another form of definition of the greatest common divisor. Namely, it says that for two integers, not both zeros, D is the greatest common divisor of these two integers if and only if the following two conditions are satisfied. The first one, it is a common divisor of A and B. And the second one, instead of saying that it is the greatest, we say a little bit different thing. If C divides both A and B, then C divides D. Previously it was C small or equal than D, now in alternative form divides. That is addressing this irregularity in the proof and making it clear what this was about. That is also a way to define the greatest common divisor. So you may therefore relate this condition to that every common divisor divides the greatest common divisor. So the first condition is the same, the second is altered. I suggest you to look up the proof of this corollary in the book. And basically, they pay attention here and unfold everything in quite lengthy but simple argument. Because this is if and only if. There are two parts of the argument, and I will not add anything meaningful to what the book does here, so I skip the proof of this corollary and instead jump to next theorem, which is much more important for us now. The following theorem (1.4) in the book is crucial for the proof of the fundamental theorem of arithmetic, which we want to analyze the argument how it is proved. Theorem tells us that if A divides BC and the greatest common divisor of A and B is 1. Another way to say that the greatest common divisor of two integers is 1, they say two integers A and B are relatively prime. They have greatest common divisor of 1. That's just a small piece of terminology. Then A divides C. So A divides a product, but has nothing to do, no common factors, in fact, with one of the factors. So it must divide another factor. This is instrumental for the proof of the fundamental theorem of arithmetic, and let us see how it follows from our alternative characterization of the greatest common divisor. Proof. AB, the greatest common divisor, is 1, implies that 1 can be presented as an integral linear combination of A and B. That 1 equals AU plus BV for some integers U and V. Well, indeed, greatest common divisor is the smallest among positive linear combinations of this shape. 1 is the greatest common divisor. 1, we must be able to present 1 as in this shape, as AU plus BV. As soon as we have this, we multiply it by C. So for some integers, this identity holds. C equals ACU plus BCV. I multiplied everything by C. This is still true. Now we know, it is the assumption in the theorem that A divides BC. A divides BC. By the definition, what does this mean? BC is equal to AR with some integer r. BC is an integer. It's a product of two integers. It is an integer. A is a divisor of BC. BC is A times an integer. So I use it here with this BC and rewrite C equals ACU plus AR instead of BC. V. And I factor A out. C equals A times Cu plus Rv. All four C, U, R, and V are integers, so Cu plus Rv is some integer. C equals A times an integer by the definition of divisibility means A divides C as required. So that is what we wanted to prove. A divides C, we proved that, yes, by definition, this is same thing as C is A times some integer. Thank you for listening. We will continue.